Morning everyone, hope everyone's well. Just had to do a frantic reboot, so I think I've got everything working at the moment, but we'll find out as we go through. So, starting a new topic today. So far I think we've got Lily, Tanishka, Nico, Adam, Ruby. Good to see you online. We're going to start looking today at Chemistry 3, which is Quantitative Chemistry, and it's the one that a lot of people don't like to start with because it's quite maths based. But once you can get your head round the systems we're going to use, and I'm going to use lots of scaffolding as we're going through, because I think when we're looking at quantitative chemistry, if you just can get into the habit of doing the same thing every single time, then actually when you go into an exam and start doing the questions, it becomes a lot more straightforward because you drop into autopilot. I remember I started doing this when I was at secondary school, I did it through college, and I'm still using exactly the same techniques all the way through when I said at college and my chemistry degree at university, and I'm still using it now. I've been tutoring some A-level chemistry recently as well, and the same techniques apply whether it's at GCSE or whether it's at A-level. So we're going to take it nice and slow. We're going to try and look at the background behind it, and there's not a great deal of content here, which is brilliant. If you think about the ecology topic we've just done, there was 6 lessons worth. This won't be anywhere near that, but it's really important that you understand the fundamentals and that you can then apply them. So today we're going to start looking at some of those ideas, some of those rules, some of the ways of answering questions. And then as we work our way through, we'll look at some different exam questions as well. So let's move on. Morning, Jack. Good to see you online as well. I want to start off with this concept of a mole. And I don't mean the little furry animal that digs up gardens. What I'm talking about is it's a unit of quantity that we use in chemistry. So now let me just put that down, because it's one of those things a lot of people look at and they just cannot get their heads round. So let me just put down unit of quantity. We're quite happy saying, I want a few apples for 3. I want a dozen eggs for 12. If we're talking about a century, we know it's 100. A couple is 2. These are words that we use in everyday language. Now, the term mole means exactly the same thing. The problem is, because the number is so big, we don't actually use it pretty much anywhere apart from chemistry. So I'm going to put the number down here. So we're looking at 6.022 times 10 to the 23. Now, it's a huge, huge number. And realistically, anything apart from atoms, and it starts to get into a little bit ridiculous when you start looking at actually what a mole is. But it is just a number. And the thing is, by using this number, we can start talking about, we can actually count atoms, and we can make sure we've got the same amount of atoms. And you'll see how that's important as we go through. But if I'm talking about a mole of something, it just means I've got that many of them. And that's as simple as it gets. And like I said, it should be no different than saying I've got a dozen eggs. I've got a mole of atoms. I can have a mole of eggs as well. To be fair, a mole of eggs would probably give you enough eggs to make a new planet. But you sort of get the idea that we're going with this one. So it is just literally a quantity. Try not to get too brain fried when we start looking at this term moles. It's just a number of something that we've got. But like I said, it's such a big number that we just don't tend to use it very often. The reason we use it is because actually what we want to be able to do is, if we're doing a chemical reaction, and it's sort of leading into the next part of this lesson, if we want to do a chemical reaction, we need to make sure there's no wastage. So we need to make sure that when we're reacting chemicals together, we have the right amount to make sure it reacts fully. So one of the things we use moles for is actually, if I've got a reaction, and let's just do something fairly simple, such as this. So magnesium plus oxygen forms magnesium oxide. Morning, Chris. I've gone from this one because it doesn't need balancing. But what we've got is I've got one atom here. I've got one here, and I'm making one molecule. So if I had a mole of magnesium, it would react with a mole of oxygen, and it would produce a mole of magnesium oxide. Now, the really useful thing about this, and if you've got a periodic table somewhere at home as well, it's well worth having a look at those. It'll be in all your textbooks, or you can find them online afterwards. But we're going to be using periodic tables quite a bit. I'm going to bring up in a moment the AQA one. In fact, I'm going to do that now. I completely forgot to do that a minute ago. So let me just go down and bring up the periodic table that you guys will use. And we're going to use this quite a bit. So let me just rotate that round and make it bigger. Like I said, we're going to go really slow because I want to make sure that you can actually get your head around what's going on here. So this is the periodic table that you will get in the exams. Now, we know, or hopefully you can remember, from when you did Chemistry 1 and Chemistry 2, and it also tells us on the table here that the big number is the atomic mass. Now, the reason that's useful at the moment is this atomic mass, if I was to put a gram sign after it, would tell us how much 1 mole of that element would weigh. Okay? So, for instance, if I take helium, if I had 4 grams of helium, I would have 1 mole of helium atoms. If I was to take, let's go for calcium, if I had 40 grams of calcium, that means I would have 1 mole of calcium atoms, which would mean I would have, oh, hang on, it's still not the wrong one, that one, I would have this number of them. Okay? So by weighing them, we're actually effectively counting them as well. So this is quite useful because actually we know for a fact atoms are too small, and we don't actually want to count them. Well, we couldn't physically count them ourselves. I mean, I've done a similar thing though in other sort of experiments. Those of you that I've taught for radiation before, I often use Skittles. So what I end up doing is I give groups of students 100 Skittles between them. Yeah, I'm going to go through this a few times, Tanishka, to make sure that we've got it. Okay, so I'll go through it again, and then if you're not sure, do ask on this, because I want to go really slow, because getting these fundamentals in now, if you can do this, the whole of the rest of this topic is easy. But it's making sure that you really understand. So all of you, as I'm going through, do ask for questions, do ask for clarification as we're looking at this. And obviously I will definitely do the Google Meet after this because it's really important. Now, I was just saying, so some of the, when I was doing the radioactive decay experiment, one of the things I did is I give groups of students 100 Skittles. And the idea is, it's just basically to form a probability curve. And they pour the Skittles out, and they count the number of ones with the S showing, and they get rid of the others, generally by eating them. And they work their way through. But when I'm giving those cups out of 100 Skittles, if I've got, say, 7 or 8 groups in the class, which I may well have, I don't want to have to count out 700 or 800 Skittles. So what I normally do is I count out 100 and I weigh them. Because that way, after that, if I weigh the same amount of Skittles in another cup, I know I've got 100 Skittles. So very, very quickly, I can just put a cup on the scales, weigh out 100, and I can do it very, very fast. And that's literally what we're doing when we're actually weighing out atoms. Okay? So I'll just give you a couple of examples again. If we look at carbon, carbon's atomic mass, and if you don't believe me, I'll just put it up here. Carbon's atomic mass is 12. So that means that 1 mole, which is this many atoms, equals 12 grams. If I take helium, helium's atomic mass is 4, which means 1 mole equals 4 grams. Okay? Now, I know we're looking at atoms, and I think the reason that people struggle with this is because you can't physically see an atom. It's not something that we can pick up and use on a regular basis. But actually, if we take this into a slightly different sort of scenario, let's imagine we're sort of counting eggs. And I wonder if I've got a picture that I can do to go with this. Let's just see if I can quickly Google and see if I can get some images. There we go. This one might do. So let's bring this picture up. So we can see over here, we've got all of these different size eggs from different birds. This one over here is an ostrich egg. Never tried eating an ostrich egg yet. And then we're sort of working our way down. We've got some turkey, we've got ducks, and the sort of chicken down here. So you can see the size difference. Now, if I had a dozen chicken's eggs, so where's my chicken? That one there. I would have 12 eggs. If I had a dozen ostrich eggs, I'd have 12 eggs. The thing is, the ostrich egg, because it's so much bigger, is going to weigh so much more. So I would expect my mass to go up. And if we look at atoms, and we'll do a bit of a sort of revision here of Chemistry 1, we can see the same thing. So for instance, if I look at helium, we've just said that helium, we've got 4 particles in the nucleus. Let's draw my atom out here with 2 electrons around the outside. Now we don't tend to worry too much about the mass of electrons, but I've got 4 particles in the middle. If we then go through and choose something like, let's choose lithium because it's fairly small. Lithium has 7 particles in the nucleus. Three of them are protons, which means the other 4 can't count today. Hang on, just get rid of that one there. There we go. It means the other 4 are going to be neutrons. So we'll just put our electrons round just so we've done it as a bit of a recap. And if you can't remember how to do this, go back and have a look at Chemistry 1 at some point, not now. But if you have a look, I've got 4 particles in the nucleus of my helium atom, but I've got 7 particles in the nucleus of my lithium atom. So I would expect my lithium atom to be heavier. So in other words, 1 mole of lithium would equal 7 grams. Okay? So what we're saying is that by weighing out our atoms, we can work out how many atoms we've got. So try not to overthink it. It's exactly the same as using the word dozen, except rather than counting things like eggs, we're actually counting atoms, okay? And the periodic table gets given to you in the exam, so you have all of these masses. And it's just down to the fact that some atoms are bigger than others, so are going to have a greater mass, which means if I want the same number of them, it's going to weigh more when we put it on the scales, okay? So, let me have a quick look at how we can sort of develop and use this before we start looking at some equations. And again, if that's really unclear, please do stop and ask which bits you're not sure about as we're going through. Or you can ask it later on as we sort of go into the Google Meets. But all we're doing is counting atoms by weighing them out. Now, let's have a look at something like carbon dioxide for a minute. So carbon dioxide is that. And if you remember from when we looked at covalent bonding, that would mean there are 3 atoms in this molecule. I've got 1 carbon and it's attached to 2 oxygens. Okay? Now, if I wanted to count the number of these, I have to work out something called the formula mass. And we actually call it the relative. Done again. There we go. We actually call it the relative formula mass. Yeah, Lily, that's absolutely spot on. 1 mole of an atom is the atomic mass in grams. Okay, and if you can remember nothing else but that today, that's going to help you so much as we go through and do some of the other calculations with this, okay? So that's the most crucial bit. What we're going to do is we're just going to take that from an atom and we're going to put it into a molecule so we can use exactly the same idea to count molecules rather than individual atoms, okay? So that's the next bit. So again, let me know if you've got this as we're working our way through. If we take something like carbon dioxide, this is my formula. I have 1 carbon and I've got 2 oxygens. So the way I would suggest doing this, and we're going to look at several molecules now, and I'll put some other ones up on the Google website, sorry, Google Classroom afterwards so you can practice some of these. And the best way of doing it is just to practice loads and loads of molecules. You could literally just go onto Google and just Google, give me lots of different types of molecules, and then just work out the atomic mass. And Wikipedia will always tell you what the actual mass is afterwards, so you can check if you're right. But it's quite a good skill to try and learn, because once you started doing this, this becomes really easy. So let's look at CO2. I'm going to write down carbon. Carbon's atomic mass is 12, and I have one of them. So 1 times 12 equals 12 grams. We'll do the same thing for oxygen. Oxygen's atomic mass is 16. There's 2 of them. So 2 of them are going to have a mass of 32 grams. So if I add these together now, I have a mass. So my formula mass, and we often use the symbol MR for this, my relative formula mass of carbon dioxide is 44 grams. So 44 grams of CO2 equals 1 mole. Okay? Because we're now looking at a molecule rather than the atoms. Let's look at a few other molecules as well, so you can start seeing how this works. And again, if there's bits you're unsure of, please do ask, because this is probably the topic a lot of students find the hardest, but it's also the one that if you put the most effort into, it's really quick marks in the exam for it. But you've got to spend the time trying to make sure you understand it. So let's have a look to start with. Let's choose water. I'm going to go through exactly the same working out as I did before. I've got a hydrogen atom. The atomic mass of hydrogen is 1. And I have 2 of them. So that's going to equal 2 grams. I have oxygen, which we said was 16. I only have 1 of those, so that's going to equal 16 grams. So I add them together. So 1 mole of water is 18 grams. Let's choose one slightly harder. Let's choose sulfuric acid. This is one of the acids that you need to know. So I'm literally going to sit and go through it exactly the same way as we just have. Hydrogen, the mass is 1, and all of these, I'm just getting off the periodic table. You can't see it on your screens at the moment, but I've got the periodic table on another monitor so I can see these. And in the exam, you will always, always, always be given the periodic table. So you don't have to memorize any of these masses. I know a lot of them because I've been doing it for years, because I'm getting a bit of an old git now. So actually, I know these just from practice. Okay? But you don't have to worry about that. You just have to look at the big number. And on the AQA periodic table, it's the number at the top. And it even tells you that on the periodic table. You just have to take that big number and write it down. So, hydrogen, I've got 2 of them. 2 grams. I also have a sulfur, but I only have 1 of them in this molecule. So the mass is 32, so that's 32 grams. I've then got oxygen, which we know is 16, and I've got 4 of them in this molecule. 16, 30, that's 64. Do correct me if I make a mistake on this, because I'm doing it in my head because I haven't opened up the calculator yet. So we've got 4, 6, 8. So therefore, 1 mole of sulfuric acid is 98 grams. What other molecules shall we choose? Let's do one with brackets so we can see how that works. And please do stop me if you're looking at this going, I'm really struggling, I'm not sure. But tell me which bits. Don't just say I don't get any of it. Tell me which bits if you are. Or actually, if it's making sense, again, let me know because that'd be really good. So this bracket means that everything inside the brackets is multiplied by the number outside of the brackets. So magnesium has a mass of 24, but I've only got 1 of them. So that means I've got 24 grams in my molecule. Oxygen we said was 16, but I've got 2 of them. So that's 32. And hydrogen, I've also got 2 of them. So that's 2. 4, 6, 8. So 1 mole of magnesium hydroxide is 58 grams. Okay, I'm going to do one more. That's quite tricky. I'm glad you got it. Like I said, if you're looking at it going, oh, get a move on with it, I'm trying to go through and repeat the same thing to make sure it's... Because actually, with all of the calculations in quantitative chemistry, there's only a few calculations you have to do. And it's just doing the same thing over and over again till you're so sick and tired and bored of it that you can do it pretty much in your sleep without thinking about it. And that's what we're trying to get through to here. Right, I'm going to do one now that's a lot harder. It's going to use exactly the same techniques. And if you understand this one, you've nailed it. What I would suggest is just go through and practice some different molecules. So let's do ammonium sulfate. So ammonium sulfate is that. So if we go through and do the same thing, right, remember everything inside the brackets is multiplied by the number outside of the brackets. So I've got nitrogen, the atomic mass is 14, and I've got 2 of them. 28 grams. I've got 4 hydrogen inside, multiplied by 2. So that means I've got 8 of them in total. So that's 8 grams. Over this side, I've got my sulfur, but I've only got 1 of those. And I've got my oxygen. So if I add these up now, 8, 16, 18, 22, 6, 9, 10, 11. So 1 mole of ammonium sulfate would equal 112 grams. Okay? Sorry, Nico, if you need to go back and watch this later on, absolutely fine. So realistically, if you can do this one, that's about as hard as it's ever going to get in the GCSE exams, because we've got brackets, we've got numbers inside, but the actual system to use makes a lot of sense. What I would recommend is after this video, go through these and do an annotate one of them. Have I added up? I might have added up wrong. Hang on. 4, 6, 16, 18, 22. Should be 112. Let me just double check. I may have made a mistake. It's very easy at the moment. Yeah, it's 132. Well done. I'll work out where I made the mistake in a minute. See, this is why in the exam, always show you working out. Because if this was worth, say, 3 marks in the exam, I would have still got 2 of them for showing the working out, where I'd only have lost 1 for getting the wrong answer. And this is why I don't do things in my head normally. My mental arithmetic isn't hugely great. So, yeah. I haven't made a mistake on that one. Oh, I'll work it out in a minute. Anyway. Oh, I know what I did. I didn't add that 2 on there. That one there. Thank you. Okay, so yeah, what I was saying is choose one of these, go through if you've got these listed out, and then annotate round it steps. So step 1, do this. Step 2, do this. Make sure that your revision notes are so good that if you didn't look at it for 3 weeks, and hopefully you will, the next time you look at it, you can look at your notes and work out exactly how to do this. Okay, that's what your revision notes are like. Should be like. If you look at your revision notes and they don't make sense, there's not enough detail in there. Okay, yeah. And the brilliant thing, Lily, is you will always be allowed a calculator in the science exam. So yeah, fantastic. Let's move on. Let's get rid of that, and let's just move this over to there. Right, so the next sort of step with this then, we've gone through those sort of masses. Now what I want to just have a look at, just to see if this makes sense, I'm going to go back to my carbon dioxide, and we've just said that the molecular mass of carbon dioxide equals 44 grams. Okay? I'm not going to go through that again because you've got it in the notes a little bit just further over. Now, if I was to break the carbon monoxide up, we know that we would end up with 12 grams of carbon, and we would end up with 32 grams of oxygen. Okay? Because we said over here, is it going to work? Yeah. We said over here, where was it? Up here, that we've got 32 grams of oxygen, 12 grams of carbon. Now, this is 1 mole of CO2. If I was to break it up into individual atoms, I would end up with 1 mole of carbon, but I would end up with 2 moles of oxygen. Okay, so we just go through that again, and then I'll sort of put the formula down that I'm using for this one. If I was to break up 1 mole of carbon dioxide, I would end up with 12 grams of carbon, but 32 grams of oxygen. Now, we know that 1 mole of oxygen is 16 grams. So if I've got 32 grams, I must have 2 moles. Okay, so what we're looking at for the formula for this one, and let's just change colour because it's really important. So moles equals mass over and the atomic mass, or moles equals the mass over the molecular mass. Okay, depending on whether we're looking at molecules or whether we're looking at atoms. So for this one over here, moles equals 32 grams divided by the atomic mass equals 2 moles. So make sure you've got this formula down somewhere. We're going to be using it a lot, and hopefully it sort of makes sense. But that's the sort of the base formula that we're using for this as we work our way through. So let's sort of take this and start having a look. Let's go over this side for a minute. Let's start having a look at chemical equations and actual reactions, because at the end of the day, as chemists, that's what we do. Biologists obviously study lots of living things, how they interact, and they sort of look at a lot of what chemists do, and there's some brilliant sort of discussions on this. Physicists, they're looking at the physical world, they're looking at forces, they're looking at energy, but often they're looking at what's theoretically possible. When it comes down to actually making things and making it happen, it's usually the chemists that end up doing that. And a lot of it comes down to these chemical reactions that we're going to be looking at now. And there's lots of chemical reactions. And actually, if any of you sort of worked your way through chemistry as a future career with this, and I thoroughly recommend doing it because you will always have work because they're crying out for chemists. A lot of the time, what it's looking at is how molecules interact with each other so we can work out how to make new molecules. We're not going to do that now. What we're going to have a look at is how can we work out how much of something we need to have for a reaction to occur. Okay? So let's choose something like, let's choose a really simple one to start with. Hydrogen plus oxygen makes water. Great experiment, this one, when we do it in a science lab. Because actually, if we fill up a balloon with a mixture of hydrogen and oxygen and set light to it, we get the most incredible bang. It goes off bang really quite spectacularly, so it's a fantastic one to do. But literally, all we're making at the end of it is water. Now, if you have a look at this one, I have 2 hydrogen atoms over here. I have 2 oxygen atoms over here. But on this side, I've got 2 hydrogen atoms, but I've only got 1 oxygen. So theoretically, if this was actually how it worked, I've had an oxygen molecule that's just magically disappeared into thin air. Now, as scientists, we know that cannot happen. Yeah, even when we're looking at magic on TV, there is something going on which is tricking us into making us believe something else. Okay? Not sure what you mean, Lily. What do you mean by which formulas for atoms? Are you talking about the moles? If we're talking about moles, we're looking at this one here for atoms. Okay? Because it's the mass divided by the atomic mass. Right. So we're sort of getting onto this bit of where we have to balance equations. And again, it's one of those things that students go, oh, I can't do that. Do you know what? No one can do it when they first start doing balancing equations. There is not a rule that I can give you that you go, I'm going to follow this rule every single time and it's going to work. There's very, very few people anywhere that is naturally can look at the balancing of equations and just do it. For most people, it's a case of practice, practice, practice. And I'm going to put some worksheets on the Google Classroom afterwards for you to be able to practice how to do this. It's a bit like if you're doing crosswords, if you're doing Sudoku, if you're doing any form of puzzle, it gets better with practice. What a lot of students do is they look at it the first time and it doesn't work for them and they go, I just can't do it. I obviously just can't do it. Where actually, I've to sort of go through some of these with teachers, and sometimes the teachers get it wrong because they haven't practiced for a while. So we'll start off with some really basic methods of doing this, and then we'll gradually make it a little bit harder and we'll sort of take it further and further and further. Okay? And that's probably where we'll end up finishing today, because it'll be a really good point so we don't end up frying your brain too much. Now, if you can imagine, what if we had a line going from this arrow, just working our way down. I need to make sure that I have the same number of atoms on each side of this line. Because if I don't, either atoms have magically appeared from nowhere, or they've magically disappeared into thin air. And we know that's not going to happen. So what we do need to happen is we need to make sure we have the same number on each side of that line. Okay, I'm going to change the way I've laid this out slightly, so I'm just going to get rid of what I've just done for a minute. I've got no idea why that red dot's not moving for me, but anyway, it works. Now, in fact, let me get rid of this as well, and let's do it as a bit of a table. I know for some of you that you like making your work really neat, so you can actually draw this as a bit of a table. So let's just do that now. I'm going to draw a line underneath. I'm going to draw a line going down here. I'm going to draw another one here. And I'm going to draw one coming across. So I'm going to do it as a bit of a table. I know they're not straight, and some of you are going to be sitting there cringing slightly, but it works. So, hydrogen and oxygen. I'm going to list the atoms that I've got in my chemical reaction. I've got 2 hydrogen here. I have 2 hydrogen here. I have 2 oxygen here. I have 2 oxygen. Sorry, 1 oxygen on this side. Now, we cannot put a number inside of a molecule. If we do that, we end up changing the molecule into something completely different. Okay, which means we've got a different chemical reaction. And I'll show you what I mean. If I take water, if I was to put another oxygen on here, this one is water, this one is hydrogen peroxide. Okay, this one we drink and rely on for life. This one's toxic, but we use for bleaching our hair. Just by adding one extra single oxygen on. So we cannot put a number inside the molecule. That's a big no-no. The only place we can put numbers is in front of the molecule. And when we do that, we multiply the whole molecule by that number. So what I'm going to do is I need another oxygen on this side. So I'm going to put a 2 here. So I've now multiplied my whole water molecule by 2. So that means I've now got 2 oxygens, but I've also changed the number of hydrogen. And again, this is something students go, oh, obviously that can't work because now the hydrogen doesn't work. That's fine. I can deal with this. So the oxygen now matches. So what I'm going to do is put a 2 here. And that now works. Okay. So sometimes you'll do this. You'll get in a big muddle and it doesn't work. That's fine. Cross it out. Start again. Have a go from a different stage. And you'll see this with some of the problems I'm going to give you in a minute. Okay, it really is trial and error, and I promise you, you'll get better with practice. Let's have a look at another couple, because we've got about 10 minutes, and I want to make sure that actually you're really happy with what I'm doing here. Okay, so let's choose this one, and this is one of the ones on the worksheets that I've done in a minute. Well, I'm going to give to you in a minute. Sodium plus water. This is a brilliant experiment. So there we go. This is the experiment that you can do in a science lab. You drop the sodium, it fizzes round, it often catches light. If we've got a universal indicator in the water changes colour and it can pop. So it looks like proper chemistry is happening, okay? So I'm going to do the same thing again. I'm going to draw my table. I've now got 3 elements in here, so I'm going to do 3 rows. You don't have to make it look this fancy in the exams if you don't need to, because at the end of the day, this is just for your working out. So I've got 1 sodium. Change colour just so we can see what's going on. I've got 1 sodium. I've got 1 oxygen. I've got 2 hydrogen. 1 sodium here, 2 hydrogen, 1 oxygen. On this side, I've got 1 sodium here. I've got 1 oxygen. But look, I've got 1, 2, 3 hydrogen. This doesn't work because actually the problem I've got is I've got an odd number of hydrogen over here, but an even number over here. We can still get there though. So remember, we can only put numbers in front. So the first thing I'm going to do, I'm going to try putting a 2 here. Now, you can try lots of different methods, see what works. Now I go through and work out what effect this has. So 2 sodiums, 2 oxygens. I've now got 2 hydrogens here and 2 hydrogens over here. So I've got 4 of those. This now looks like it might start working. So let's see. Let's put a 2 here. And a 2 here. And it works. Okay? So it's trial and error. We're working our way through. And like I said, I have lots of worksheets. You can practice as much as you want on this later on. And it really is practice. Let's choose the next one down. Let's come back to our friend hydrogen peroxide that I told you about a moment ago. So hydrogen peroxide, yes, we bleach our hair with it. It's fairly unstable. And over time, it actually degrades. And it breaks down into water and oxygen. Now, if you want to ever speed this up and really, really annoy your hairdresser, if you're going to have your hair bleached, just put a piece of potato in their hydrogen peroxide because it causes it to degrade almost instantly. So they end up with absolutely nothing apart from a bucket full of water that won't bleach your hair. I wouldn't suggest doing it because it will really irritate them. So, hydrogen, oxygen, 2 hydrogen, 2 oxygen. Let me just change colour again. 2 hydrogen, 2 oxygen, 2 hydrogen, 3 oxygen. If you can't see where I'm getting my numbers from because I've gone a little bit quicker, just let me know. Right, let's see how this is going to work. We can put the numbers in front, remember? So let's start off by putting a 2 here and see what happens. That gives me 2 times 2 is 4 hydrogen. I've now got 2 oxygens here and 2 oxygens here. That makes that 4. Just put a 2 there. One more. And what I will do is I'll start next week's session on Monday with balancing as well. So we have a little bit more practice just to make sure we've got this. And then what we are going to do next time as well is we're going to combine the balancing with the molecular masses you've just done and take it into a proper exam question. And if you can do that, and I know all of you will be able to because actually you seem to have understood what I've done so far. Brilliant. Let's have a quick look. Let's go down and choose one that's, well, which one should we do? Let's do this one. So another molecule that breaks down into potassium chloride and oxygen. It's even too skew for me, that one. It's better. So I've got 3 different atoms, so I need 3 rows. There we go. So I've got potassium, got chlorine, and I've got oxygen. Remember, when you're looking at these, absolutely vital, because you will lose marks in the exam, every element starts with a capital letter. So I know I've got 3 elements because I've got 3 capital letters. This is actually a lowercase l. It's not an I for iodine. But so it's really important. In the same way as in English, if you don't put a capital at the start of a sentence and a full stop at the end, you would lose marks. In chemistry, it's the same. You must start each element with a capital letter. So if I add these up, 1 potassium, 1 chlorine, 3 oxygen. 1 potassium, 1 chlorine, 2 oxygen. Now, 3 will never divide into 2. So what I'm going to do, I'm just going to double this first molecule. Count them up. 2 potassiums, 2 chlorines, 6 oxygen, 2 times 3. Right, I've got too many potassium on this side and not enough over here. And I can put a 6 there. And again, that works. Okay. Hopefully, that has made sense. Like I said before, the reason that we balance these equations is every atom we start with, we must also finish with, okay? We can't suddenly magically lose or gain atoms. So as a chemist, the first thing we do is we balance an equation to make sure that all of the atoms in the reactants end up in the products. And then once we've done that, we can then progress to the next stage. If you guys get these, then in the exam, these sorts of calculations, not the balance on its own, but where we're going to next week, are generally worth 4 to 6 marks. Okay? However, with a bit of practice, you can do them very fast, and you're pretty much guaranteed the marks if you follow the same system all the way through. Right, I'm going to finish there today, because what I don't want to do is show you too many new things and you forget. I'm going to go onto Google Meet in a few minutes. As always, I'm going to drop the link into Google Classroom. If you've got any questions, come and ask. I will also, onto Google Classroom, put some other examples of these questions, some different worksheets for you to have a go at. But go away, practice, 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 and then have a great weekend. Okay? So I'll hopefully see as many of you as possible online in a minute. Well done, guys. Have a great weekend.